Yeah, fine. So yesterday you guys enjoyed a lot, so today you'll have double work because I'll also be doing some homework. So
Really getting 6 yesterday.
yeah, but I hope you remember your colleagues were working till 9:10 yesterday, right? So today you will be doing that. Okay. Yeah. So what are we going to do today? So today we will be understanding the basics of gamma spectroscopy. So do you remember yesterday's class? I'll be testing that your knowledge from yesterday's class, and I think you should not speak much today. Any experienced people in gamma spectrum? No. I'll separate them. all all the participants who have already analyzed gamma spectroscopy stand in one side and okay. So today I will test your knowledge from yesterday, and we will give you some samples. We will analyze some samples, and ultimately we will get some efficiency values. Okay. So without wasting much time, we'll start the session. So initially, I will be running couple of samples, and you will have to identify the peaks. What are the peaks that are found in gamma spectroscopy? No. In one, for example, I give you lead peak. So in a lead peak, what are the different peaks that is present? Photo peak and Compton peak and backscattering peak and X-ray peak. Okay, X-ray peak we might not be able to get, but rest of the peaks you have to, and there is one more peak. There is one more peak. No, think. No. Think. No, a coincidence is okay. Yes, annihilation. So DA people should not speak much. Okay. So this is a sample source, cesium-137, 4 kilobecquerel is the activity, which is not much, as you know, but it will give you a fast counting and will get some spectrum. So if you use a soil sample for this same source, I'll have to keep for 1 day. So initially, let us see what are the peaks that we get from cesium-137. Cesium. It's a point source. Okay. Basically it is for safety. So see, I can handle it safely like this. Yeah, red gloves. Those gloves.
Can we
Other letter.
No, because otherwise
See.
the other question is like you have done the calibration with respect to that while something like that.
No. The thing is, see, how do I handle this point source? So this is very small. It can be lost, and you know the problems with the lost source. So for example, people from DA already know, you might be already knowing, if you lose this source, for example, you have paid something to BAERB and you have procured the source, and somehow, somewhere you have lost it, you have to report it as soon as possible, and they will check once in a while. They will come, I think, once in for 2 years or 1 year, or once in a while, I don't know the time period, they will come and check how many sources that you are already having. So suppose if you miss, you have to report it, and a lost source is a big headache. It's not even enough if you pay them back about the source, or because you don't know where it has been lost, you don't know what are the consequences of it. So you have to be very careful with this source. So what we do, how do we maintain here, is by having a separate locker room for all these sources, and we make an entry on who has taken it, and he has to return it as soon as possible, and if it is missing, he is the one who is responsible for the source. So this is about source handling. So point source can be lost anywhere, but this is easier to find. So that is the only concern. And point sources we don't use for calibration, except for energy calibration. Efficiency calibration by using point sources of no point, correct? So you will understand what we are speaking. We might be speaking Chinese now, but after this class, we might be in the same. Yeah.
There are so many consoles like this now.
Yeah.
So all these point sources you have kept in separate.
Yes. All the point sources are in separate bottles, and it is labeled. it is labeled and it has its activity values, the date of, so you can see that sealed gamma source, cesium-137 procurement, what is that? They give an activity and they give it on a date. So this is 4 kilobecquerel on January 2023. Okay, so suppose if I measure today, this may not be 4 kilobecquerel. Cesium has a long half-life, relatively long half-life. It might be around 3.8 kilobecquerel. But some other sources, let us say cobalt has a half-life of 5 years. So after 2 years, it might be like 3/4 of the original. So we need, yeah.
Iridium will be less.
Yeah, there are other sources. Iodine is even less. Iodine is like 8 days. So you need to know, so when you're getting a source, you need to know the activity, on what date the activity is given. And so that is why we have given all these details. So now when you are going to keep a sample inside a gamma spectrometry, detector inside this lead shielding, I've explained all this electronics and these things in the first class. Okay, now what are the care that I should take? So initial care is that, as I mentioned earlier, there should be not even a speck of dust in this sample. Can you tell me the reason? Yes, if a speck of dust goes inside, it is very difficult to remove. I don't know where the dust is. I can put IP, I can wash it again and again, but I might not even find it. So when you do the MDA calculation, you can see that even one count can give you a higher minimum detectable activity, and that will affect my counting. So what we want as operators of a detector is the lowest detection limits possible. For example, the samples, geological samples, you have very small volume and you will have very low activity. This one, environmental samples are also having very low activity. Then if my MDA is higher than the activity present in that, so I cannot report it. So that is why we should always keep it close, never open it unnecessarily, and when I'm keeping it in, and I should wash this thoroughly. So now the last batch asked me one question. So you are going to analyze. No, that is acetone. Okay, IP or acetone, something that dries too quickly. So I wash it all the way. So the last batch asked me one question, peculiar question. You are using soil samples. How can you ensure that there is not even a smallest amount of dust in this bottle? How do you ensure that? How do we do that? No. So that is the reason why we are using the slippers in this, so that the dust doesn't come in. The main reason is that we don't do the sample processing and counting in the same lab. So the sample processing lab is separate, and dust samples are not even processed in this building at all, not even in the lab where you went yesterday. So the dust samples, the soil samples are processed in a laboratory outside of this building, where it is sieved and removed all the dust particles, unnecessary items like roots, these all are stones are removed by using 2 mm mesh, and then again sieved by using 450 micrometer mesh number 42 or something, I'm not very sure. Then we seal it, because cesium and all are more attached to the clay particles than to the soil particles. So there is some things like that. So then we seal it, clean it thoroughly over there, and take it to the lab above for for the equilibrium to happen between radon and its daughters. Okay, that is important, that we have already explained. I am not going to explain in detail. If you have doubts, you can ask later. So we seal it and keep it in lab. There also one amount of washing will go through, and from there, when it comes here, it will be already clean as this. Still we clean it and keep it inside, so that 3 or 4 times it is cleaned thoroughly, so the bottle doesn't contain any kind of dust particles. Because once a small amount of dust goes inside, it is very difficult to reduce the MDA. Okay, so this is the basic laboratory cleanliness and laboratory routine that we have to see. Okay, now the high voltage is set. I have explained already in the first class, high voltage is set, amplifier is set. We don't have to do anything afterwards. Now what I have to do is that first thing, calibration. What is the first calibration that we have to do? Open that sheet of paper. First calibration that we have to do is energy calibration. So what does this energy calibration mean? I have to check whether my peak is in the right place. For example, if you are using a cesium source, this is a cesium point source. Where should I get my peak? 661.6. What if I get it in 665? It might be some other radionuclide. If I get it in 609, it is bismuth 214. So then even if my sample has cesium, I will identify it as bismuth 214. Do we want it to happen? No. So we have to check whether it is proper. So let us check. So I have used cesium 137. So you can all come closer. Okay. So I think you need to have some space for them. So this is a software, Genie 2000 software. We have renamed as Gamma Acquisition and Analysis for our use. Okay. And I open, keep a chair in the detector number 2, MCA. Okay. So now this is when I open, I get a window like this. You have already seen this software, right? You know how to open a detector. So can you tell me how to open a detector? File. Okay. You have opened the same software, alpha spectrometry. No.
MCA.
No. Open the data source. Open data source. Yep. And now select detector. Okay. Then you have 2 detectors over here. So this is our detector, detector 01. Okay. So what we have to do? File, open data source. So this is for this this software. You might be using other softwares as well. Okay. So that will have different source. The first thing what we have to ensure is that your detector is what you are seeing here. So detectors controls are there. Okay. Now I am getting detectors control. I get start, expand, clear. All these controls are activated. Correct? Now let us set the time. So how to set the time? Setting time. Yesterday you have done the same experiment.
There we set the time and
Oh, no?
before on the pump.
Okay, display.
No, MCA.
Yes, okay, MCA and
Acquire setup.
okay, acquire setup. Okay,
That
you have time.
Yeah.
Okay, so I'll set, since this is an active sample, I'll set it to 100 seconds. Okay, let us see how the peak comes. So I've set, this counting has started. You can see that peak is starting to form up. So I'll just put expand on. So this is the peak that is starting to form. Okay. So you can see the peak over. So this is a zoom window. You already know. So where is the peak? It is exactly at 661.6. So the photo peak is correct. Okay. If not, one channel 661.7 or 661.8 doesn't make big difference. So it is in that peak. So my energy calibration is perfect. So I don't have to worry whether my results, whether the identification of the radionuclide is proper or not. Correct?
So actually, you are placing this point source to identify whether the
Yes,
calibration
is
correct.
correct.
Or
Yeah,
not.
yeah. So if this is not right, what I will do is that I will play with amplifier.
Okay.
I will change the amplifier settings. I will change the gain settings in order to make this fit into the curve. So suppose it is over here. I have super fine gain or fine gain that quartz gain. So to shift this to this location. But once you do this, if your detector amplifiers are all working fine, you need not change it at all. You just have to give the bias voltage. Once you give the bias voltage also matters very much. So bias voltage should not vary. So once you set a bias voltage, the same bias voltage should be there throughout the lifetime of the detector. Or if it changes, you have to change the amplifier settings. So here I am giving a plus 4699 volt. That is 4.6 kilovolt. That is set from the day this detector has come to this lab. So it is not at all changed. Okay, and all the other parameters also need not be changed. It will be like that. So that is why we have put a sticker on the other amplifier. Can you see that? Please don't touch. Can you see that? So that is a manual amplifier. So because we have set that parameters, so even if a small modulation is done on the amplifier, then this thing will not come here. Okay, so this point is clear. Now you have to identify. Can you show me the peaks? Can you show me the peaks? So I'll put an expand over here. Can you show me the peaks? Compton edge. Where is the Compton edge? This is Compton edge, correct? This is Compton edge. Where is your photo peak? Photo peak is here, 661. Where is the other peaks? Annihilation peak. Where is annihilation peak? No, it is not visible here. Okay, 511. There is no annihilation peak because it is short counting time and already the baseline is very much high. So Compton, where is backscattering peak? Backscattering peak is somewhere over here. Can you see? On small, yeah. No, it's 186 somewhat, I think. Okay, somewhere over here you can find your backscatter. There is an X-rays are beyond this, beyond these areas. Okay, so there is one more peak over here. I think this should be also backscattering. So you identified whatever the peaks that are there that we have that was explained. Is there any peaks that is missing that we have discussed and we are not able to find today? What peak is missing? Annihilation peak. Okay, annihilation peak is not visible. Any other peak? X-ray you cannot see. One more peak. Not backscattering peak is somewhere. One more peak. No. Something. Yeah. This one, it is copper coated. So what do I say? The rebound is much less. Okay. So there is one more peak. Think. Which is not present in this sample, but it would be present in some other sample. In this sample, it is not there. In some other sample, it is there. I want you to tell what is that peak. No. Nothing related to that. It is related to the gamma spectrometer itself.
Pair production.
No, that is annihilation. Think. Okay, you think. I'll keep another source and then you find out that peak. Okay? Bramstalling is again X-ray. X-ray is, see, X-ray because we are not going below 30. So, maybe it's a summation peak. Yeah. Why some peak is not present in this sample? There is only one. So if there is two peaks that is produced, then it will add up and you will get some. Yes. So let us see. If you are getting that peak here. Okay. So somewhere you have forgotten everything, but somewhere you remember also. Okay. So let us see. So this sample is cobalt 60. So where should I get the peaks? Cobalt 60. 1.1. 1.1 what? MEV. KV? Okay. So let us check. So I have a peak over here. So this is 1.17, 1.1171. Correct? 1173. Okay. And what is this? 1. Okay. Down ಮಾಡ್ಲಿಕ್ಕೆ ಆಗುದಿಲ್ಲ. Share ಇದು. 1.3. 1332 keV. Okay. So we are getting both the peaks.
1.13.
Okay.
1.17, 1.13.
Yeah. Yeah, two peaks. And where can you identify the Compton peak? 1.33 and 1.17. MeV.
Average is 1.25.
No, some peak. It is not average peak, it is some peak. So why does some peak come? Because at a certain period of a detector, both the peaks are, just remove this. So at a certain moment of a detector,
Constant peak and some peak are same or different.
coincidence, it's same.
Because we said coincidence peak.
Yeah, some peak. Yeah, coincidence peak, some peak. Yeah. So what happens is that at a certain moment, as sir explained in the last class, yesterday's class, at a certain moment of the detector, let us say the resolution of the signals are produced in nanosecond range, whereas the MCA has microsecond range or something like that. So in a second, when you get two peaks of 1171 and 1332, it two adds up. So we get one peak, both the peak addition. That is what it is called as coincidence peak or some peak. So it is over here, 2.505.
So coincidence peak and some peak are both the same?
Same. It is same, right, sir? Coincidence peak and some peak are same, right?
Coincidence peak.
And some peak. Summation peak.
It's a
It's
summation peak.
yeah, it's the same thing. Oh, so I hope this much is clear. So can you identify the Compton edge over here? Where's the Compton edge?
Third one.
Here, somewhere over here is,
Back.
yeah, there are like two Compton edges or something like that. And what else do you find? Is there annihilation peak?
0.5, what is
511. What is the energy of annihilation peak? It should be there in 511. Why 511?
the same amount energy?
Rest mass of energy of electron is what?
257.
Yeah, it's 1 point. It should be, it is a pair production peak. It's a pair production. It is half of rest mass energy of an electron. What is the rest mass energy of electron? 1 point. 2 into 5 point. It's not 511. 1.012 or something like that. Oh, yeah, something like that.
1 mega electron.
So half of the rest mass energy of a electron. So it should come somewhere around 511. So let us check. So here it is not that much visible, but your samples it is definitely visible. You can see in your spectrums that we give later. Okay? So this much is clear.
One more question.
Yes, ma'am.
Here 1.17 and 1.33.
Yes,
peaks are
yes.
taken forward, both are equally probable. 100% probable, right? 100%. Every time abundances, I am talking in terms of.
Yes, it is 100%.
Correct. Then why that, which peak is more? I think the first peak is shown more compared to second peak. If you see the area under the curve also, first peak will be more. Area
I don't think so. It must be almost similar. It should be almost similar. So you don't
Yielding will be different.
no yield is same, no? Yield is same. Yeah, it will not be similar, sir. Yes, correct. Efficiency is less. Yes, sir. Efficiency is less. Efficiency decreases as the energy increases. So counts will not be same. Yeah. I'm sorry. Thank you, sir, for saving me. I would have. Okay. So shall I remove the spectrum? Yeah. Okay. So we will start. I will show you a sample spectrum developing of a uranium sample. Okay. Then, but you will see how long it takes for a uranium sample, like the uranium RGU. Yes. Okay. So this is RGU. So this is what we call it as RG stands for 1 minute. Reference material uranium. Okay. So reference I'm not very sure. It's actually IAEA reference material RGU, and it has a code name of RGU1 and RGTH1. I think so. Can you take that file over there? Yeah, I'll show you the exact. It's in the first drawer. There is a file. Yeah. Yeah, you can get it in Google. Okay. So I'll keep this inside and I'll then show. Yeah, this is uranium. Okay.
It's completely fixed.
No. You can see that there is some gap because this was first made in the year. I'll keep it inside and I'll then explain. You can see that there is some gap. Okay, I'll explain the reason for that gap. It is not advisable to have this gap as per our last thing, but you also forgot me to tell me something. I've not cleaned this sample. Give me that isotope. Actually, I had cleaned it yesterday, so it does not require cleaning again, but it's best to have a standard operating procedure that you clean it every time. You assume everything is dirty. So, okay, so I have a dustbin over here, so I'll just throw it. So I have cleaned it, you can see. So I just homogenize the sample. No. Yeah, I think this is fine.
It should be plain.
Yeah, it should be as plain. Yeah, it should be. It should be homogenized. So if you fill it to the brim, you don't have to worry about homogeneity because it will not move much.
See,
Yeah.
actually you are keeping to this much level
No,
standard as well as sample.
I fill the sample and to the brim. But I'll tell you the reason why I could not fill this to the brim. So this sample was produced in the year 1960s. Okay, this sample you don't get now. For example, I'll take you the reference material sheet. So people asked me how, last class also they have asked me, like how do you do it for different samples? For example, if you have sand, for different densities, because we have this much standard materials. So each one is different. So we have so many pages, and in one sheet we have separate 3 or 4 files. So we might have like 10, 15 or many more. I have not counted. So I have reference material for different geometries of different samples. You bring me vegetable, I have vegetable standard. You bring me, I think even milk powder, we have a standard, but it is not radionuclide, I guess. We have standards for elements, elemental standards. We have standards for soil, sediment, water, filter paper, sea plant ash, and clove, spinach. So many things it is there. So you can see that this is the IAEA RGU1 uranium ore. So this release date is 1987. So this is not available now. So I tried to order it, I did not get. So the activity of the sample is 4940 becquerel per kg as of 1/1/1987. But what is the half-life of uranium-238? 4.5 billion years. That is how I understood the age of the universe. Yeah, it is not 1,600 years. I could even hear 12 years somewhere. Okay, so let us see the spectrum. Yeah, uranium is the presence of the uranium. The daughters of the uranium confirm that at least Earth is 4.5 billion years old. That is the main reason to say that Earth is 4.5 billion years old. Okay, because so much of its daughters are present. So I don't know the exact scientific meaning, but the presence of uranium daughters is how we say that Earth is 4.5 billion years old. Okay, so you can see that for 100 seconds, you basically don't see any spectrum. Right? Do you see anything? No, it's almost 50-60 seconds. And you might get some 1 or 2 peaks here, but can you analyze anything? It's all baseline. Can you see this? Can you see this? What I'm trying to say. So see, I have 1 peak over here. This is 609. Okay, but that I can analyze. But what about the rest? So this is 351. There is 1 peak. Okay, I agree. 295. Okay. But nothing else. Some peaks are there, but it is pretty much smaller. So what we do to get good peaks, we increase the counting time. So basically we keep it around 30,000 seconds for soil samples in HPGs. In sodium iodide it is around 10,000 seconds. So if still the resolution is not good, if the peak is not coming, if your sample weight is less, so what should I do? I should again increase it. So I can go for 60,000, 82,000, 85,000, 1,50,000. So I have done, so till what level should you do? That's another question. So how to find out the upper limit? So what I do is that if in a soil sample, if I don't find any radionuclides up to 82,000, then I'll say that it is below the minimum detectable levels. Okay. If in vegetable samples, I will go as much.
That time, what will be the weight of the sample?
That is depending upon how much sample you have taken. So it is your sample. How much sample you have given, that is. So sometimes if the sample size is very small, for example, you could not get enough samples. In that time, we should say that it is below the minimum detectable activity for so much counting time for so much grams of sample. So that information is important. What counting time, what amount of weight. Okay. So basically this is it. So now I hope till here everything is clear. Any doubts? Any doubts till here? No. So now I will open uranium spectrum. So we have 3 HPGs, 3 high purity germanium detectors. So in 3 germanium detectors also I will open a uranium sample and give it to you for you to analyze. Okay. You will individually have to mark, I will show you how to mark a region of interest in one sample. Basically you have to mark region of interest for the samples that are listed. Do you have the list?
Yes.
Okay, so you have the list, right? So you have to calculate the region of interest, area under curve, and all those necessary details. And then I will give you the activity of the sample, and then we can calculate the efficiency. So is this much clear? Any doubts till now? No. Yeah, that we will have to take 36. That is because I will tell you how, why, okay. It is because of the branching factor. So if you don't consider the branching factor, and if you take 99, your graph will not come up. That you will understand in the end, okay.
The Compton
Yeah.
at what electron, what energy?
That you can see.
You can
No. Compton peak is corrected in this. Yeah, one more thing is that in any gamma spectrometry, it's just them, right? Yeah. So in any gamma spectrometric analysis, you usually get a Compton peak or Compton addition of Compton. What do we say? Not Compton correction. We do it later, but there is some contribution of Compton. So what is that thing? So if I have to explain it in an easier way, it's something like these peaks which are on the end, which are on the last. A higher energy, in the sense towards the higher energy, those contribute some Compton energy, some Compton peaks to the peaks that are behind them. For example, the last peak in thorium series that we analyze is thallium 208 at 2614, okay, which is abundant, which I have taken. Now that 2614 peak will contribute some Compton active counts to the peaks behind it, which is bismuth 214 at 191764, K40 1460, and this bismuth 214 at 1764 will again contribute to K40. So that is why you're getting graphs if you had seen this graphs properly, you could get like the baseline decreases. Yes, at the end baseline becomes 0. Initially it will be also higher and higher because of these Compton contributions. So you have to correct it for it. Okay, so there are Compton correction formulas. Some of you have used it, but this system gives you the result corrected for these Compton corrections. Yeah. Okay.
That's really easier to do.
Oh, okay, but we use this spectrum. It's okay, sir. Once I finish it, we can show it then.
Not like that. You can set there this one so that the entire curve on that one.
Okay.
You have to just set that.
I think display it is somewhere in display.
Display.
preferences, yeah. So I can just background, spectrum background is,
RGB change.
wait,
RGB.
okay.
All is that.
Okay, white and
This one.
reference spectrum blue,
Okay. Blue, take this one, this.
and just gives blue. Okay,
Fill.
yeah, but I prefer the other way around. So the other way around is much easier for me because I can see individual counts. So this is another way to look at your spectrum, but I think Ortec gives similar results, right? But you can see the peaks, but individual counts is better in the other round. So we can set it any way we want.
You put it normal.
Yeah?
Normal.
Yeah. Wait a minute.
This one. Instead of full.
No. I think.
Color will do it.
No. I'll have to reset it. So spectrum background I'll have to make black, and reference spectrum. What was reference spectrum? White? No.
It was yellow.
It was yellow, right? Okay, fill, normal. Okay, no.
Change that one.
Wait.
Background.
Background was black, and reference spectrum was yellow. It should do this. Yes. So yeah. Now where were we? I explained about Compton correction. So this spectrum, this software does the Compton correction for you. For example, now I will show you how to set an ROI, region of interest. Then you will understand the Compton correction file. So initially I have set some region of interest. I am clearing it all. So now the first peak, what is the first energy that you have to analyze? It is,
K40.
look at the energy, which is the first energy.
First energy wise it is
46.5.
46.5.
Okay, so 46.5 is somewhere over here, correct? So this peak is not perfect, correct? This peak has been not counted for enough times for the spectrum to be developed. So, but again I'll try to put an ROI over here, so or else I'll open a better peak. Okay, file, I'll go for Genie 2K cam files 138. 138.8265 gram, which you will have to consider while doing the calculation later. And this is the counting time. So now please pay attention over here. So wait, 138.8265. 138 gram basically, that's enough. Okay. So this is your you can see here you have channel number, counts and preset time. So you know which time to take. Better to not confuse by here I have stopped the counting at 26,968 seconds. So you can actually take this one, live time over here, 26,968 seconds. Okay. No, you have to take it on your own later, not mark it now. Okay. So now I will remove all the ROIs over here, and then so you can see the peak properly, right? So you know how the peak is developed. It is put into different channels, right? So each channel, so you can see this channel has 988 counts, and it goes higher, gets to the peak and then drops, correct? So you want to put two markers. You have already seen how to mark, right? So here I have to check I'll make as big as possible, and then I'll check the bottommost part. So I have to put the point where the peak is just getting ended and the next peak starts. So this is okay, and here I can see that I can put it over here, and then I'll go display ROI, add ROI. So this is how we do one ROI. Okay, now here you get two, if you can see there is integral area. So basically there is 67,896 counts of this peak, integral counts. But the Compton corrected count is 36,987. So you have to only take this value, 36,980. So it corrects your sample for Compton effects. Okay.
Counts is nothing in the gross count.
Integral counts is Compton corrected counts. Okay. No, integral is gross counts. The area is Compton corrected counts. So when I made a mistake, everyone jumped on me. Okay. So 4 of you can sit here, analyze this peak. 4 of you can sit in another one. 4 of you kids can sit in another one. So we will start this exercise. Okay. So now it's up to you.
Why the sample is not up to the grip?
Because I did not have enough samples. So they gave us, I think it was 500 grams of sample. We have 3-4 geometries. Okay, then this was the end last some sample. So I could only get 138 grams. Yeah. Tagoli. So you can take chairs, as many chairs. One chair is over there. You can take that. Yeah. Yeah, counting it ಬೇಕಾಯ್ತಾ?
The gamma lens used. This is the gamma lens for 46.5.
Yes, so I have it in here. Okay, 2024 I end RGU. Yes, this is all yours.
Display ROI.
Display ROI and expand will give you this zoom in area. Yeah, I have cleared ROI, display ROI, clear all. Yes. Okay, now you set up the ROIs, you can zoom in, zoom out. Okay, yeah. So yeah. ಇದು ತುಂಬ ಹಳೆತ್ತು. So
Yeah, it's in gel.
no, it is 238 gram, man. So we'll use 138 gram because everyone is using 138, or else efficiency would be confusing. 1 minute. Open file location. 142. Okay. Oh, okay. 6 August. No. Date created 22.
Come here.
9 down already.
ಅಲ್ಲ ಅದೇ
Seconds.
It's not a race. Okay. Display ROI. Clear all. Okay. Now you do. Hey, 1 minute.
Background count 0 na?
Allah. Background counts will take later. It's not 0. Keep one chair here so that nobody goes near this detector.
Okay.
Okay. So, and you can take one chair, I think you. Can you bring some chairs? Okay. There is one chair over there.
The point is that actinium emits X-rays too.
Okay.
Their energies are these two,
89 and 92, 93, yes.
around, yeah.
Yeah.
But the point is that in some cases, if this peak is big, what happens?
9/11 peak.
Yeah, it happens so that these gammas and these X-rays are in coincidence.
Okay.
What means that if you calculate the sum of 911 plus these two. Coincidence peaks goes just here and here. So, what does it mean? If you calculate uranium activity on the basis of this 1001 peak, it's incorrect.
Yes, yes.
Now you can see here. So, ratio of the intensities of these two coincidence peaks is 0.61.
Okay.
So, if you multiply this peak area here to this 0.61 and diminish this number for this peak area, then you get the correct number. So,
Okay.
point here is that because this protactinium peak is usually very, very small, and then you report something. If you do not check,
9/11.
yeah, and especially if you find this 1004 peak, then you have to take it into account, which may in some cases have a notable effect. Even that it might happen that you report the presence of uranium and there is non-uranium.
Did you publish this?
No.
It should. You should.
Well, I think that if you want to publish, I can advise this.
No, I don't know any details of this. You can publish. It's nice. It's very important information to be known.
Because this is a decay scheme of actinium. It is really complex. And I found this phenomenon.
I think I should switch it off.
Around 1 month ago.
This is the
Before that, please check 583.
You might have. Your detector showed that X-ray.
Actually, it will come for thorium sample. Since thorium is not there, don't worry about this. For Bismarck,
5 to 1 committee. No, you can speak as long as you want. Happy to listen.
That's what Dr. Roy was telling. There will be vacuum seal the transportation. Why? Because
See the 587 it is. Not
Roy, you can use this chair.
So what happens is,
Is it 238? I think it is 238. Yeah, 238.
So we don't have to see this peak.
No. You have to see and tell me why I did not recommend that peak for you.
238.
Yeah. Why? Can you see, sir? Find out.
maybe that I should that energy some other I should have been having.
Check. It's there in the spectrum.
There is then
Yeah, there is one more peak nearby. So that contribution can come to lead 212. So then our counting might be different. So we already have thallium 208 and bismuth 214. Sorry, thallium 208 and actinium 228. So why should I go for this difficult peak?
Yeah, correct.
So that is the logic. So whatever is a good resolved peak with high abundance, those peak is what we are taking. Bismuth has so many peaks. See, 609 is there. 1171 is there. 1768 is there. 695 is there. 794 is there. So and many other are there. So which one should I take? So if someone asks that question, which is having higher abundance and which is having proper resolution, like there is like 2 peak separation should be there. It should not be some other peak should not come and join with us. So those things we take care of. Yeah. Background I'll give. Did you do all this?
Yeah. Except K40 and
CZ137. Okay.
these are not
Yeah. Okay. Done.
He will give you, sir will give you that
2614.
K40 and
Take it.
CZ137.
Control left.
No, that is wrong. That is wrong. It is not. That is not the correct way to do your RA. So you have to do this.
Okay.
You have to do this and bring it over here. And now see. Now you can properly attach the lower marker. Or else you can no. Or else you are putting it in the half of the spectrum. See, your point was over here. Got it? So if I see from here, it looks that this is the end. But look at now. It is up. So this is the proper way to put the ROI. Okay? So you change all the things. So show me the way you are putting ROI.
We reduce it.
No, 1 minute. I'll show you. Just tell me whether you are doing.
This peak.
Yeah, if you are doing that way, you should do like this.
Oh.
And
Now
you
how you
should
read that? This way?
see this.
Okay.
I'll see where is your ROI. This one? This is your ROI?
Yes, sir.
Okay. No, this one is okay. Let me check. Only one ROI.
Yeah, we cleared.
You should not clear. You have to save it for the background. You should not clear it.
Okay, fine.
Okay.
Four more. We'll
Okay. You will do it. Okay, you do it.
Ah.
Now I'll tell you how to properly. ಅವ್ರ ಹತ್ರ ಹೇಳಿ clear ಮಾಡಬೇಡಿ ROI ಇದು. Okay, okay. So now I'll show you. So you take this peak. So now, supposing you put ROI from here. So this looks your left marker, correct? And this looks your right marker, correct? 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 Control plus R. But now when you zoom out, okay?
Don't clear the ROIs, okay? You have to save it for background. Same thing. ROI.
Okay, 1 minute. Okay. See, now you have underestimated 2-3 counts. So it should have been like this. So you have to zoom out as much as possible, or you have to make it as smaller as possible, and then take the ROI. Or, yeah, if you don't do that, what will happen is that it will be somewhere over here, and this marker will be somewhere over here. So look at it. Now you look at the peak. See, it looks from here, it looks fine, but it actually should be over here. Okay. So that thing.
We have cleared now, so.
So you started.
Again from
Yeah.
the beginning.
Beginning you do that.
Check it. What is the number? First week we check it.